Well, hello there, everybody. Welcome again to another review session by me, Mark Rosengarten, here on my YouTube channel. This is topic 1.03, precision and significant figures. Now, last time we took a look at measurement, and we took a look at how people spent a tremendous amount of money getting equipment that will measure down to very precise values. Today, we're going to see why that's the case. Now, you ever try to round off answers to a math problem? Usually your teacher will tell you, oh, round to the nearest 10th, round to the nearest 100th. Well, after this, you will never, ever have to ask where to round an answer off to. Today, I'm going to show you exactly what significant figures and precision are, and then next video, you'll see how to apply them in rounding off answers to math problems. And therefore, here we go. Now, the importance of proper rounding. As you know, a chain is only as strong as its weakest link. Pardon me. And a team is only as strong as its weakest player. And of course, the answer to a math problem can only be as strong as the weakest measurement that was used as a variable in that problem. So if we take a look at this problem, for example, we have 23 divided by 1.73 equals OMG. Look at all those digits. Where are we supposed to round that off to? Well, as a result of this video and the next video, you will know exactly why you rounded off to 13. 23 has two significant figures. 1.73 has three significant figures. You always round to the fewest sig figs. 13 is two sig figs, and therefore 13 is where you round it. Now, if that's confusing, good, because I haven't taught you how to do that yet. So let's look at that now. So you have to make sure that your answer is only as good as the worst measurement that went into the math equation. Because if you make your answer more precise, it's going to give a false sense of accuracy that may have bad consequences down the road. So, what is precision? Well, as you saw in the last video, precision is the place you record your measurement to. It's one place smaller than the device is marked to. We use precision to round off answers to addition and subtraction problems. So how do we figure out the precision of a measurement? Well, if the measurement has a decimal point in it, then the precision is going to be the place furthest to the right in that measurement. So, for example, in 23.004, there's a decimal point, right? It's right here. See, it's a decimal point. And actually, it looks more like a square, but that's okay. So the place furthest to the right, that's three places past the decimal, that's the thousandths place. That would be the precision of this measurement. And in 0.3320 grams, again, there's a decimal point. So the place that's furthest to the right, regardless of what's there, that's four places past the decimal, that's the 10,000ths place, is the precision of that measurement. For 330 decimal point, what a weird way to write 330, but there's a reason for it. 330 without a decimal point would have a precision of only the tens place. Putting a decimal point is telling us that 330 is precise right to the ones place. Putting that decimal point after a zero, if you want to show that that zero in the ones place was measured, is going to be one of the trickiest things to remember, and yet one of the most important as well. So that's the precision. So what if there isn't a decimal point in the number? Well, if there's not a decimal point, then the precision is either where the integers run out as you go from left to right, or if you want to show that a zero was measured and not a placeholder, we put a line over that zero to show that it was measured. So, for example, 23,000 centimeters, we run out of integers at the thousands place. So this measurement was made to the nearest thousand. But what if we want to show that the measurement was made to the nearest hundred? Well, we put a line over the zero in that hundreds place. This shows us that the 2, the 3, and the 0 were measured, and these zeros are placeholders to keep the number the size it is. This measurement goes to the hundreds place. And what if we want to show that it's 23,000 to the nearest tens? Well, then we put a line over the tens place to say that the 2, the 3, the 0, and the 0 were measured, but this final 0 is a placeholder that we put there to keep this number this size. And that's how you can find the precision of any measurement. Now, if you want to see this over again, since this is on YouTube, just rewind it and watch it again. Significant figures are used for rounding off answers to multiplication and division problems. Significant figures is the number of digits that were directly measured with the measuring device, which means any digit except placeholding zeros would be considered significant figures. Now, we may abbreviate significant figures as sig figs or SF because significant figures, I mean, that's a lot to write. So SF will always be the abbreviation for significant figures. So, number of significant figures in a measurement equals the total number of digits from and including the first or leftmost integer, that's non-zero in the measurement, all the way to the limit of precision of that measurement. So, for example, since this number has a decimal point, the precision is the thousands place. So from the first integer all the way to the end, the number of digits in that range is the number of significant figures. There are 5 significant figures in this measurement. Because the first integer is the 2, the precision is where that 4 is, so all the digits are sig figs. And by the way, there's a rule that may make this a little easier for you. If a number is 1 or larger and there's a decimal point, then every digit is a significant figure. Or as I like to call it, bigger than 1 with a decimal point. They're all sig figs. Go ahead and check my YouTube video entitled Big Sig Fig Gig, and it will give you additional examples. Now, this number here, the limit of precision, there's a decimal point, is the last place. So that would be the 10,000s place. From the first integer, that's the 3, to the 0, that would be 4 significant figures, 4 measured digits. 330, bigger than 1 with a decimal point. They're all sig figs. That makes it a little easier to determine. Shall we look at some more examples? Okay. 23,000 with a decimal point, bigger than 1 with a decimal point. They're all sig figs. This number here, it's bigger than 1, but there's no decimal point. The precision ends with the line over the 0. From the first integer to that precision, right there, would be 1, 2, 3 sig figs. In this measurement, we go one place further with the line over the 0. So from the first integer to where the precision runs out, that's 4 sig figs. And then in this example, there's a decimal point, so the precision is this last place. So from the first integer to that precision, there are 2 sig figs. The numbers in front are placeholders and therefore do not count as measured digits. Bigger than 1 with a decimal point. They're all sig figs. Okay. And this covers pretty much every example that you might come across when you do a measurement. And that is how to do precision and significant figures. I hope you enjoyed it. I hope you found it useful. And until next time, this is Rosengarten Reviews Chemistry, 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 Chemistry.